start today's lecture. But before starting the new things, I would like to revive some of the concepts we discussed yesterday. We discussed tensor analysis, different types of tensors like covariant tensor, contravariant tensor, mixed tensor, and then we learn about the raising and lowering the indices, and then we discussed covariant derivative, Lie derivative, etc. So, if you have any question from the previous lecture, please you can ask. If there is no question, then we continue the first section, Riemann geometry, and today we will finish this concept. The most important concept in Riemann geometry is the Riemann tensor. In fact, this is the most general, this is the tensor we use everywhere, like in general relativity, because if there is no curvature, then it means we have a flat space. So, special relativity in fact deals with uniform motion. So, there is no concept of Riemann curvature tensor. However, when we take care of the curved space time, then we need curvature. And for example, let us think of a paper like say I have this paper, it's like a flat paper. If we put something in this paper, for example, I put some weight, say a mass, it will get a little bit bent, and then we put another mass, it will get more bent. So, in fact, this bending means we have a curvature and we have bent the flat space to curved space. So, this is the effect of curvature or the curved space time. So, how to measure this curvature? We carry out a vector along two distinct paths on a curved surface to the same point, and we get different results. If we have the same result, it means we have a flat space. So, mathematically we can say that this can be measured by the difference of these quantities, like this is a vector, we take a covariant derivative with respect to c, then covariant derivative this with respect to d. So, this is the quantity which is measured through a on curved space through one point, and this is another point, and when we take the difference, if this difference is 0, then we have flat, and if this difference is non-zero, then we have a curvature tensor. So, this is the I am not going into the details how to calculate it, how it is derived, but I am just putting the expression here. In a curved space of n dimensions, same formula holds, but this quantity is called Riemann curvature tensor, this R, A, B, C, D, and A, B, C, D can run from 1 to 4 if we are considering space time, and this is 1 to 3 if we are just considering space in 3 dimensions. So, it depends upon the dimensions what we are taking, it is 3, 4, or even we can extend it to n dimensions. So, generally we can write the Riemann curvature tensor as you can see. This is in terms of the Christoffel symbol. So, it means we need the basic ingredient, the metric tensor, to calculate the curvature tensor, because through metric tensor we can calculate the Christoffel symbols, and then we can write the curvature tensor. Another thing you can see, this curvature tensor involves the second derivative of the metric tensor. Here I shall explain some of the identities coming from the curvature tensor. You can see these 3 identities. This is the combination of 3 different curvatures, but it is obtained by cyclic permutation. Similarly, the second expression is obtained through the covariant derivative, and this is obtained by the contracted index B. These identities were derived by Bianchi. So, for his name, these are called first and second Bianchi identity. This is first, and this is second Bianchi identity. And the third one is called contractive Bianchi identity, because we have a contraction of the index B here. Now, this curvature tensor has the anti-symmetry properties in the last two indices. Say, if you are considering the RABCD, and you can see that if we interchange this CD by BC, we have a negative sign. So this means this is the property of anti-symmetry. However, we can explore more properties of the this tensor if we lower the index. For example, we have RABCD, and we can calculate R if we multiply it by, say, A and E. So this A will be contracted by this, and we can have E, B, C, D. So this is also a Riemann tensor, but this is easy to analyze this quantity. We can see that from here, this is antisymmetric through this index if we interchange AB by BC. Similarly, if we interchange the CD with DC, then we have symmetric properties. So this is pairwise symmetry. I mean, we have interchanged the two indices AB and CD simultaneously. So in other words, you can say this is a symmetric tensor if we have a two pairwise interchange of the indices. So we can write the Bianchi identity in terms of this tensor as follows. We have just lowered the index. So some more quantities can be derived through the Riemann tensor. If we take the contraction of the Riemann tensor, that this is the Riemann tensor. We have taken C, I mean this same index. So it means these are contracted, and we have left only with AB. So this is called Ricci tensor. So in other words, Ricci tensor is obtained by contracting the first and third index of the Riemann tensor. Obviously, this tensor is a symmetric tensor. If we interchange A and B, we have the same quantity, no difference, no negative sign. Another tensor, which is, this is a scalar quantity, a Ricci scalar, can be obtained by taking the contraction of RAB with GAB. So this is a scalar curvature, and this is obtained by GAB. Now you can you have seen that we have obtained from RABCD the Ricci tensor, then Ricci scalar. So if this Riemann tensor is 0, then definitely this implies Ricci tensor is 0. Then definitely this implies Ricci scalar is 0. However, the converse is not true in general, but in a particular case it can be true. So this 0 means we have a flat space time, and we but RAB 0 doesn't mean we have a flat space time. Okay. Next we come to the concept of curvature invariants. Curvature invariants in fact are obtained through the Riemann tensor, and this is very useful concept to check the singularity. So Riemann tensor is useful for determining whether a singularity is essential or coordinate. Now let me define the essential and coordinate singularity. Essential singularity is the singularity which cannot be removed, that means it is essential. Coordinate singularity is the choice is due to the bad choice of the coordinates. So if we can have very good coordinates, then we can remove that coordinate singularity. So if the curvature becomes infinite, the singularity is essential, and we can define the scalar quantities that remain invariant under coordinate transformations. So constructing scalars from the Riemann tensor, we could check if they become infinite somewhere. Of course, infinitely many scalars could be constructed from the Riemann tensor. We'll see this one. Like we have constructed the Ricci scalar from the Riemann tensor, then Ricci tensor, and so on. However, symmetry consideration can be used to show that there are only finitely many independent scalars. All others can be expressed in terms of these. So thus we need only to construct the simplest scalars, and the first one is the Ricci scalar as given here. This is the Ricci scalar, and the next one you can construct through the contracted Riemann tensor, and similarly we can construct R3. These are all scalar quantities. So we need to check for the singularity purpose that whether it remains finite or not. If it is finite, then we have no singularity, but if it is infinite, then that means singularity exists. So if the independent curvature events defined above are all finite, the singularity will be coordinate. If any of them is infinite, the singularity will be essential. Now we come to the example, and I would like to give details of this example. So I would discuss the Riemann curvature tensor for the metric which is given as follows. This is the metric of the on the surface of the sphere. In fact, what we have done, we know that x1 is equal to r, x2 is equal to theta, x3 is equal to phi in spherical polar coordinates. However, we are fixing here the radius as a. So this is constant. It means our first coordinate becomes constant. So we are working on the surface of the sphere. So we are left with only two coordinates, x2 and x3. So we redefine these coordinates in this case, and so we have x1 is equal to theta and x2 is equal to phi. So this is the metric, which is in fact in general this metric is for this is in 3 by 3, 1 0 0 0 r square 0 0 0 r square sine square theta. But when we fix the radius, this metric reduces to in this form. Here we have two-dimensional case, and we can pursue further. For the sake of simplicity, I have taken this metric. Otherwise, we can go for 3 and other dimensions. So I would like to give some details about this metric. To find the Riemann tensor, you need the values of the Christoffel symbol. So we first calculate the Christoffel symbol. I just gave the values of Christoffel symbol. I am not calculating these, but these can be calculated very simple. Obviously, this is symmetry. So then 1 2 2 1 is equal, and 2 2 is 0. These are the 0 Christoffel symbols. And non-zero can be found like this: 1 2 2 is equal to minus sine theta cos theta, 2 1 1 is equal to cot theta is equal to 2 2 1. So these are the non-zero Christoffel symbols. So now we can calculate the Riemann tensor. This is the general formula. As you know, we have just written down the general formula: a b d comma c minus a b c comma d plus a e c e b d minus a e d e b c. Okay. Now we I would give details on only for the one component. Rest will be the same. For example, we want to calculate 1 2 1 2. So in fact, we have taken AC fix and BD is equal to 2. So we are taking A is equal to C is equal to 1, B equal to D is equal to 2. So putting all these values here, 1, 2, 2, 1, 1, 2, 1, 1, 2, 1, 2 plus 1 E 1 1 2 D, here it should be BD, so it is 2 here, minus 1 E2 E2 1. Okay. Now we know that 1, 2, 2 is non-zero, and this is with respect to 1. 1 means theta. So we can differentiate it with respect to 1. So minus sine theta, which is derivative of sine theta is, or I just write down cos theta with respect to theta, minus 1 to 1, which is 0. So this will be 0. Then we can have the options of 1 E1, here it is E. So we can take E equal to 1, that will make it 0. We can take E is equal to 2, that will also be 0. So this term is also 0. So we are left this with term. Now we can check 1, 1, 2, here it is E, and 1, 2, 1. Similarly, we can write 1, 2, 2, 2, 2, 1. So we check this is 0. So this goes to 0 here. Then 1, 2, 2 is non-zero. So we can put here, and 2, 2, 1 is 0. So this will also be 0. So it means we are left with minus sine theta, which will become cos theta, cos square theta, and then minus sine square theta. So it means there's something here, 1 A2, and there's some mistake here, otherwise it should come to the as minus sine theta, cos theta, cot theta, and finally we are left with the answer as sine square theta. So the final answer of this component is 1, this is Christoffel symbol 1, 2, 1, 2 is equal to sine square theta. If we have the Riemann tensor, then we can calculate the Ricci tensor or Ricci scalar. So you can see that you have found 1, 2, 1, 2 is equal to sine square theta. So you can now calculate the Ricci scalar, Ricci tensor CBD comma C, CBC comma D plus CEC EBD minus CED EBC. Okay, you can put the indices according to the non-zero values of the Christoffel symbol, and we can have the following options. For example, we want to calculate only R11. You can find the rest of the indices as well. So C11 comma C minus C1C1 plus CEC E11 minus E1, E1c. Now we have the following choices. If we put c equal to 1, this will be, we can put c1 or 2, but in all cases this will give this 0, because triple 1 is 0. If we put here 2, 1, 1, 2, 1, 1, obviously we have cot theta, but with respect to 2, with respect to phi, this will be 0. So this can be made equal to 0. Next term, we can have 1, 1, 1, 1 is 0, so we can neglect it. And however, if we put 2, 2, so 2, 1, 2, we have cot theta, and cot theta with respect to theta is non-zero. And we can write the next terms, and we can see this will be 0 anyway. If we take C1, so we don't have any choice, so this will be 0. However, we can have the non-zero term from this expression. Let me write down minus. I just put C1, E1, E1, 1, then I put C2, E1, E1, 2. Okay, is equal to minus cosecant square theta. This will become plus. Now we check here. We can put E is equal to 1, that will be 0. If we put E equal to 2, then this will also be 0. So this will be 0. In the next term, we put 2, 1, 1. This is a non-zero, so we can take 2, 1, 1, 1, 1, 2 minus 2, 2, 1, 2, 1, 2. Now you can see 2, 1, 2, 2, 1, 1 is cot theta, and 1, 1, 2 is 0. So this term will be 0, and from here you can have cot square theta. So we can have finally cosecant square theta minus cot square theta. Now this is the well-known trigonometric identity, and from here we can write this equal to say, I think this will be sine square theta minus cos square theta sine square theta, and this is 1 minus cos square theta sine square theta. So this is equal to 1. So R11 is 1. You can check that these terms will be R12 is equal to 0 because it is symmetric. So this will be the same. Similarly, we can find R22 is equal to sine square theta. This is the non-zero. Now, when we have the Riemann tensor, non-zero Ricci tensor, then we can write down the value of the Ricci scalar. As you know, Ricci scalar is equal to GAB RAB. So this means we have G11 R11, G12 R12 twice plus G22 R22. So now you know that G11 is, as you know, G11 is a square, G22 is a square sine square theta, and G12, G21 is 0. So we can write here 1 over a square, and R11 is 1. So we can put here 1, and this is obviously the 0, and G22 is 1 over a square sine square theta, and R22 is sine square theta. So this will cancel out, and we can have 2 over a square. So this is the value of Ricci scalar, or you can say the first curvature invariant. You can see in the examples we have found that R is a constant. I mean, Ricci scalar is constant. So it can be generalized, and you can write it to k, where k is the constant. And in n dimension, we can write the Ricci scalar like this. So we have found that this Ricci scalar is finite. So the singularities at theta equal to 0 or pi will not be essential singularity, but they will be coordinate singularities. So I have given the idea from the surface on the sphere. We can extend it to 3-dimensional case when we consider the spherical polar coordinates. You can see from here, I am not going into the details, but you can see from this example that here R121 is 0, R213 is 0. So similarly, all the components can be calculated, and by using these we can find the components of the Ricci tensor. These are the components of the Ricci tensor. R11 is 0, R12 is 0, R13 will also be 0, and you can see all the components here. Here in this example, we have seen the Riemann tensor is 0. Obviously, this is confirmed that if this is 0, then Ricci tensor must be 0. Also, in this case, the Ricci scalar will be 0. Again, we can see that since these are all 0, so there will be no essential singularity. So all are coordinate singularities when we take r equal to 0 or theta equal to 0. Okay, now we define another concept, and this is also a very important concept. This is conformal transformation. Well, we know that transformations are always an interesting object. We can move from one coordinate system to another coordinate system, like we have taken from the Cartesian to spherical polar coordinates, or from 2-dimensional plane then to polar coordinates, cylindrical coordinates, and so on. So there are many transformations, and conformal transformation is one of the interesting transformation. This is called angle preserving scale transformation. In particular, this transformation rescales the metric tensor by a position dependent factor. So you can see from this definition that in this transformation the new GAB will be like this. So this is the new ingredient which comes in the metric transformations. So GAB tilde is the transform metric, while omega square is some position dependent function, scalar function, positive function, and obviously when the metric tensor is changed, it means everything is changed, because this is the basic ingredient in Riemann geometry. So for this reason, I would see some properties like its inverse will be like this. Here we have found that this function has raised power -2. Consequently, the Christoffel symbols will be changed, and here I would like that I show this transformation, how this comes out. So similarly, I would give the details of this thing, how this, because this is very important. We can extend the idea for covariant derivative. You can see here in this, this remains the same, but these are the extra term, and obviously if omega is 0, then these extra terms will be 0. Similarly, in terms of covariant derivative, you can see this is the same, and these are the extra terms, and in extra terms you can see the scalar function involves, and if scalar function is 0, then we have the standard covariant derivative. This is very important. We know the metric tensor covariant derivative is 0 in general, but here it is interesting in the sense that even under conformal transformation, this property remains invariant. So, in this sense, well, this can be proved in some simple steps, but I am going to calculate the Christoffel symbol, which is important. Okay, you know that this is the general formula of Christoffel symbol. AD BD comma C plus CD comma B minus BC comma D. So, this is the general formula. Now, if we calculate the is conformal, then we write like this. So, it means we are applying 1/2 AD conformal, BD conformal, CD conformal, BC conformal. Now, insert the values of these transformations, because we know that in this AB is equal to omega square GAB. So, when we insert these values, and similarly you can write GAB is equal to omega raised to power minus 2 GAB. So, we insert these values, ABC is equal to 1/2 omega raised to power minus 2 G AD, and here omega minus 2 G BD and comma C, because this comma is taken over the whole function, plus minus 2 GCD, this is plus, this is not minus, this is plus, and this is comma B minus square GBC comma D. Now, simplifying this thing, is this is equal to 1/2 omega minus 2 GAD, this will remain the same, and here you can see, you can write down, you can take it out omega square from all the terms, and you have GBD comma C plus GCD comma B GBC comma D, and you have taken the omega square outside. We have first differentiated the metric function. Next, we differentiate this one. So, in this case, we have plus twice omega comma C, and it will remain GBD as it is, plus twice omega B CD plus minus twice omega D BC. Now, simplifying this thing, we can write down is equal to 1 by AB is equal to 1 by CD GAD B plus BD A minus ABD. And you can see this is just the Christoffel symbol, original Christoffel symbol, plus the additional terms like this, minus 1 omega comma B GCD AD omega comma A CD BD minus omega comma D GCD AB. And you can see from this is just a Christoffel symbol. So we write down CAB and rest of the terms will be written like this, plus twice inverse delta CB comma A. This is the symmetric bracket, minus omega inverse omega D GCD GBA. So this is the, you can say, the Christoffel symbol when we take the coordinate transformations. Okay, so we have seen that how the Christoffel symbol changed under coordinate transformation. Next, we define on the basis of this transformation a very well known concept, conformal flatness. So a space-time is conformally flat if it can be transformed into a flat space-time by using the conformal transformation. So it is in fact interesting concept. You can transform a curved space-time to a flat space-time under this transformation. So if this can be transformed, then we can say that this is a conformally flat space-time. Next, we come to another concept called geodesic. Geodesic, you know, if we have a flat space and we join the 2 points, we draw 2 points on the paper on the flat space and then combine, if it is the shortest distance, then we say this is the shortest path on the plane. However, when we curve this page or we take the curved space-time, then we can say that this is the geodesic. So geodesic is the shortest available path on the curved space-time. Its equation can be derived as given here. Here you can see these are the derivatives with respect to arc length parameter, and this is the Christoffel symbol, and this is obviously a derivative. So this equation can be easily derived. I'm not going to give the derivation here. So geometrically we say that the vector is transported into itself. So given a vector field, vectors at nearby points are parallel and have the same length. So if we can define geodesic, we can discuss the geodesic deviation. Geodesic deviation means if two particles are moving from the same nearby points, but they cannot end up to the same point, it means there's some gap. So that gap is called geodesic deviation. So geodesic deviation describes how nearby objects are in curved space-time deviate from one another. It provides insights into the effects of space-time curvature caused by mass energy. So the relative acceleration of the deviation vector is governed by the geodesic deviation equation, which is given here. Here you can see that this is the Riemann tensor, this is the acceleration vector, and this is the tangent vector, and this is a separation vector. This is the vector which gives the deviation. If this is 0, then we have no deviation. But on flat space-time, this is always 0. This is possible only on curved space-time. Okay, now we come to another important concept. Yesterday we learned about the Lie derivative, and here we shall apply that Lie derivative to discuss isometries and Killing vectors. For example, we want to calculate the geodesic equations. I would like again solve the geodesic equation for the sphere, not in fact sphere, on the surface of the sphere, a square sine square theta. This is the simplest metric in 2 dimensions. Okay, we already know the non-zero Christoffel symbols. 1, 2, 2 is equal to minus sine theta cos theta. 2, 1, 2 or 2, 2, 1 is equal to cot theta, and rest of the components are 0. This we already know. Now we know that this is the geodesic equation. Okay, we have 2 dimensions, so we need only to put values of A only for 2. So this is in fact d square x1 ds square plus 1 bc dx. This is B and this is C. So this is B S C S is equal to 0. And the second one you can write d square x2 ds square plus 2 bc dxb dx dxc ds is equal to 0. Now we know that the non-zero values of the Christoffel symbol are here, so we can accordingly set these values. So we just write down only those components which have non-zero values. So we can, for example, here put 2, 2, 2, 2, and here 2, 1, 2 only, and it is twice because you have the same values. So twice 1 and 2. Now you can write down just equations and then we can continue. I think we have, yes, here. Where is the blank sheets? Okay. So finally, we can write down the geodesic equation in this form plus well, minus sine theta. I'm just putting the value of Christoffel symbol cos theta, and then phi dot square is equal to 0, say is number 1, and then phi double dot plus 2 cot theta and theta dot phi dot. This is a set of 2 differential equations. These are in fact ordered differential equations. Not always we can solve the geodesic equation, but in this simple case we can solve this set of equation. Well, we can multiply equation number 2 by sine square theta. So phi double dot sine square theta plus 2 cot theta theta dot phi dot sine square theta is equal to 0. Now this equation can be written as an exact differential sine square theta phi dot is equal to 0. If we open this differential, we can arrive on the same set. So Integrating it, we can write sine square theta phi dot is equal to, say, h. H is an integration constant, and from here we can write down phi dot is equal to h over sine square theta. And this is in fact d phi over ds. H over sine square theta. Now we know by chain rule that d over ds can be written as d over d phi over d theta or ds. By chain rule we can always write this thing. So inserting the value of d phi over ds from here, we have h over sine square theta d over d phi. So in fact we have defined this operator that d over ds is equal to h over sine square theta d over d phi. In other words, you can write down d over ds is equal to h cosecant square theta d over d phi. Now we put this value in equation number 1. Okay. We have that h cosecant square theta d over d phi h cosecant square theta d phi into theta minus h square cosecant square theta cot theta is equal to 0. And simplifying this, we have d over d phi cosecant square theta d theta over d phi minus cot theta is equal to 0. Now, for the sake of simplicity, we assume that cot theta is equal to u. Then we have obviously from here du over d phi is equal to minus cosecant square theta d theta over d phi. So, inserting this value in this equation, we finally arrived at this result, d phi square plus u is equal to 0. This is a very well known first order differential equation, and its solution can be written like this: a cos theta plus b sin theta. So when you insert this value into this is phi, we can calculate theta is equal to cot inverse a cos phi plus b sin phi. So in this way we have calculated the solution of this geodesic equation. But generally it is difficult to solve the system, but one can always write down the geodesic equation. We first define an isometry. This is a direction along which the metric tensor is Lie transported. So if k is an isometry, then Lie derivative of the metric tensor with respect to this vector k is 0. So in the abstract notation, we can write this equation in the following form. Here you can see this equation involves covariant derivative of the metric tensor. So if we open the covariant derivative of this metric tensor, we can simplify this equation. First, you can see the covariant derivative of the metric tensor is 0. So first term, from here you can see this term will go to 0. This is the covariant derivative of the metric tensor. Here is the covariant derivative of the vector. So finally, we can reduce this equation in the following form. And if we move further, we can also write this equation in a solvable form. So this equation is called killing equation. Why it is killing? First, this was derived by killing itself, but some people also say that it kills the equation, the result is 0. So any vector which satisfies this equation is called killing vector. We can simplify this equation in the following well-known equation, and this is the interesting equation which can be used to find the killing vectors. So next we define the wild tensor. This is also an important type of tensor, and this is in fact a combination of all tensors which we have already learned. So this is a trace-free linear combination of the Riemann tensor, Ricci tensor, and Ricci scalar. You can see the mathematical expression of this tensor. This is the 4th rank tensor. This is the Riemann tensor. Here it is the Ricci tensor, and here it is Ricci scalar. So this is a combination of Riemann tensor, Ricci tensor, and Ricci scalar, such that its trace is 0. That if we have is 0, then we can find the values of alpha and beta, and these are alpha equal to 2, -2, and beta equal to 1/3. So in general, we can write that this is the wild tensor. This is also an interesting point, that if we take the conformal transformation of this difficult tensor, complicated tensor, it remains invariant. I mean, the conformal transformation doesn't change this tensor. This is very interesting. Now we come to the examples of, well, we have already learned the geodesic equations and we have solved this. Now we come to the examples of killing vectors. You know, this is the killing equation which is usually used to solve the system. Here obviously JAB is the metric tensor, while K is the vector, and it depends how many dimensions we are taking. We are solving this equation for the metric in plane polar coordinates. So it is 2-dimensional, and we can write its equation like this. Number 1 equation which with 1 1 indices. So 1 1 comma C, and so you can take C equal to 1 because the derivative, I mean here you can see x1 is equal to r and x2 is equal to theta. So you can take the derivative with respect to 1 as well as with respect to 2. So I just expand this 1 1 2 2. Next, this is the first term, and next is the second term. Here we take plus 1 C1 comma 1 plus G12 2 comma 1. Next, third term 1 1 1 1 plus 1 2 2 1 is equal to 0. This is the first equation, and you can see from here, since G11 is constant, so its derivative will be 0. Also G12 is 0, and here G12 is 0, and rest you can see that it is 1, and you can add these. So from here you can see we have 2k1 comma 1 equal to 0, or you can say k1 comma 1 is equal to 0. So this is number 1. This is the first Killing equation. Now you can write the second, because it is symmetric, metric tensor is symmetric, so it can be written k12 or k21. This will be the same. See, on the using the same procedure, 1 2 comma 1, 1 2 comma 2, 1 1 1 1, 1 2 comma 2 plus B here is 2, so C is 1, C 1 1 comma 1 plus G 2 2 2 comma 1 is equal to 0. Now you see that G12 is 0, so this will be 0, this will be 0, this will be 0, this will be 0, and you are left with these two terms. So we have G111, so K1 comma 1 plus R square K2 comma 1 is equal to 0. This is the second equation. Third equation is K22. You can write down the third equation as K12 G22 comma 1 K1 plus G22 comma 2 K2 plus G21 K1 comma 2 plus G22 K2 comma 2 plus G21 K1 comma 2 plus G22 K2 comma 2. Now you can see this is fine, but this is 0 because G22 with respect to 2 is 0. This is 0. This is okay. This is 0. And rest is 0. This is equal to 0. So we can write G221 means 2R K1. Then this is R square K2 comma 2 plus R square K2 comma 2 is equal to 0. And finally, we can write 2R K1 plus 2R square K2 comma 2 is equal to 0. This is the third equation. So now we have three equations and we want to calculate the values of K1, K2. What we shall do, we first integrate equation number 1. So this is the equation number 1, K1 comma 1 equal to 0. When we integrate, keep in mind that K1, K2 depends upon the variable R and theta. So when we integrate with respect to R, then we have K1 is equal to some arbitrary function of theta. Here f of theta is the arbitrary function of theta. So inserting this value in equation number 2, then we can write K2 is 1 is equal to minus 1 over R square f theta theta. Here f subscript theta means derivative of f with respect to theta. So now we integrate it so that we can write down K2. When we integrate it, we have 1 over R f theta, theta remain unchanged because it depends upon theta, plus some arbitrary function of g theta, another arbitrary function. So in this way we have written K1 and K2, but we have to find the values of f theta and g theta. So now we insert these values in equation number 3, because equation number 3 involves k1 and k2. So, when we insert these values, we have equation number 3 takes the form plus 2r square 1 over r f theta theta plus g theta theta is equal to 0. This is the equation number 3. Now we divide this equation throughout by 2r. So we are left with f theta plus f theta theta plus r g theta theta equal to 0. Now we have found this equation which has two parts. One part only depends upon theta, and the second part both have r and theta. So what we shall do, we shall use the separation of variable procedure, and we take each term independently equal to 0. So in the first part we take plus f theta is equal to 0. This is the first equation, and in the second part we take this is equal to 0. Now integrating the first equation, you have the very well known solution f theta is equal to c1 cos theta plus c2 sin theta. This you know. And from the second equation you can see that this is in fact g theta theta equal to 0. So when you integrate the second equation, you find g theta equal to c3. Here obviously c1, c2, c3 are integration constant. Now you can write k1 and k2, inserting the values of f and theta. You can write down k1 is equal to c1 cos theta plus c2 sin theta, and k2 is equal to 1 over r minus c1 sin theta plus c2 cos theta plus c3. So in fact you have found the solution of the Killing equation in this case. Now the interesting and important point is how to find the generators from here, because the real application of the symmetries or Killing equation is to find the generator. So this can be done like this. You just write down k is equal to k1 partial by partial r plus k2 partial by partial theta. We have already found k1 and k2. So inserting the values of k1 and k2, then you can have c1 cos theta partial by partial r minus 1 over we are just inserting c1 cos theta, c2 sin theta partial by partial r plus k2. k2 is 1 over r minus c1 sin theta plus c2 cos theta plus c3, and this whole is partial by partial theta. Now we take the constants c1, c2 as a common factor. So from here you can see c1 and c1 theta. So c1 is cos theta minus 1 over r cos theta into partial by partial r minus c1 1 over r sin theta partial by partial theta plus c2 sine theta partial by partial r, and here plus 1 over r cos theta partial by partial theta plus C3 partial by partial theta. So you have written this equation in terms of C1, C2, C3 independently. Now you can say that you have the first generator as K1. Let's go to the next slide. K1 is equal to cos theta partial by partial r minus 1 over r sine theta partial by partial theta. K2 is equal to sine theta partial by partial r plus 1 over r cos theta partial by partial theta. And finally, the third one, K3 is equal to partial by partial theta. So this is the way one can calculate the generators from the killing vectors. So we have 3 generators, and next interesting thing is to check whether these are closed or not. So I just show at least one case in which we can prove that this is a closed system. So we calculate K1, K2 square bracket, which is by definition is K1, K2 minus K2, K1. For the closed system, this bracket must be either equal to 0 or it should contain one of the rest. For example, we have taking the K1, K2, so it must have K3. Or if we are taking K1, K3, then it should have K2 and so on. So I just can check this one. So we have already found these things. So cos theta partial by partial r minus 1 over r sine theta partial by partial theta, then K2 sine theta partial by partial r plus 1 over r cos theta partial by partial theta minus sine theta partial by partial r plus 1 over r cos theta partial by partial theta into cos theta partial by partial r minus 1 over r sine theta partial by partial theta. Now the next step is to multiply these things and check what is coming out, and we shall see in this slide that when we multiply, we see from the first term cos theta and sine theta. When we differentiate the first term with respect to r, sine theta is constant obviously, and it will go to the second term. So we can write cos theta K1, K2 is equal to cos theta sine theta partial square partial r square. This is from the first term from both sides. Now when we apply the first term to the second, then we have the following result: cos square theta minus 1 over r square partial by partial theta plus 1 over r cos square theta partial square by partial r partial theta. So we have multiplied the first term to both terms of the second bracket. Now the third term minus 1 over r sine theta cos theta partial by partial r minus 1 over r square sine square theta partial square by partial theta by partial r. So in this way, this has been written. Now we come to the second, plus 1 over r square sine square theta partial by partial theta minus 1 over r square sine theta cos theta and partial square by partial theta square. Next is minus sine square theta minus sine theta cos theta partial square by partial r square minus sine square theta 1 over r square partial by partial theta plus sine square theta 1 over r partial square by partial r partial theta. And next is plus 1 over r sine theta cos theta partial by partial r minus 1 over r cos square theta partial square by partial theta partial r. And finally, the last two terms 1 over r square cos square theta partial by partial theta plus r square sine theta partial by partial square theta. So we have opened all the terms, and one should take care of all these terms because any mistake will lead to the wrong result. So let us check. First of all, we check this type of terms. We have this one, and then we have this one, and you can see these two terms cancel out. Next we see partial square, this type of terms, partial square by partial theta square. Here you can see this should go, I mean this is here cos theta. Okay. Next is we check partial square partial r partial theta. Here it is, and there should be somewhere else. Here it is, and I think one term should be more here. Here it is. So there are 4 terms. So how can we combine? When we combine this term with this, we have you can see this is a common factor and rest is 1 because sine square theta cos square theta is 1, and here we can see 1 minus r, it is square, it is 1 over r, and yes, it is r. So here you can see minus come out, so it will be, so we can conclude that all these 4 terms will be cancel out. Now if we check partial by partial theta, here partial by partial theta and here partial by partial theta, this will be cancel out. And next is this is also cancel out. We have partial by partial r, here it is, and then it will be somewhere here. It will be cancel positive, negative. And finally, we are left with partial by partial theta. There should be some one term, I mean this with this. So we can conclude that this bracket is turning out to be K1 comma K2 is equal to 0. This is obviously an important result because we are saying that these two generators commute each other. One can calculate rest of the generators as well, but I'm obviously not going into the details, but just mentioning Okay, if we can prove all these results in any for any generators, so we say that the algebra is closed. And obviously, not all generators are can satisfy these properties. So, if for any generators these are satisfied, then it will be interesting. So, this is the way how to calculate generators and how to check its closedness. This is very important when we calculate the generators and particularly to analyze the solutions. Okay, some more examples can be done. I'm just showing that in 3 dimensions, the result obviously will be complicated. For example, in 3 dimensions, the killing vectors are the following. I'm just showing here that these are the killing vectors for the spherical polar coordinates. And obviously, one can check how many generators can be found, and you can see for spherical polar coordinates we have 6 constants. So, obviously, there will be 6 generators here, and one can check that the algebra is closed in this case as well. So, I finished the example, but before finishing or closing the lecture, I would show a video for today's lecture. So, enjoy the.
That we are two-dimensional beings living on this surface. Suppose that we want to move forward in straight lines. The equivalent of a straight line on a curved surface is a geodesic. Here, each color represents a different geodesic. In this first example, we're dealing with only a small amount of curvature. Here, each path is deflected by only a small amount. For example, the green and red paths start out close together, and they are deflected by slightly different amounts. The results will be completely different if we have a large amount of curvature. Here, notice how the red path and the green path start out very close together, but they end up leaving in completely opposite directions. This is shown for a curved two-dimensional space, and this can also be extended to higher dimensions. However, there are important considerations that need to be taken into account when applying this to the four-dimensional space-time of general relativity, and this will be discussed later in this video. Here, each color represents a different geodesic. Suppose we want to get from one side of this hill to the other. The path going directly over the hill is a geodesic, but going around the hill involves a much shorter distance. One common misconception is that every geodesic is always the shortest path between 2 points. But this example clearly shows that this is not true. It's only when we zoom in and look at 2 very closely neighboring points on a geodesic that the geodesic is always the shortest path between them. Here's another way to think about geodesics. A geodesic is the path that would be followed by a small car stuck to the surface, with its wheels always pointing directly forward, and with the wheels on the left and right side of the car always rotating at the exact same speed. A geodesic is the path that would be followed by a small car stuck to the surface, with its wheels always pointing directly forward, and with the wheels on the left and right side of the car always rotating at the exact same speed. In this next example, the different colors are all just different parts of the same geodesic. The red arrows are always the first to wrap around and create a new path that all the other arrows will follow. The red arrows are always the first to wrap around and create a new path that all the other arrows will follow. Neighboring lines that start out parallel on this surface end up converging. Neighboring lines that start out parallel on this surface end up converging. Neighboring lines that start out parallel on this other surface end up diverging. Here, every color once again represents a different geodesic. Let's now consider yet another example. The red and green arrows are not perfectly aligned with this donut. Although the red and green geodesics have very different starting conditions, they both eventually end up preferring to travel around the outside of the donut. And now, the point of no return. In this example, the geodesics that venture close to the center spiral inward, never to be heard from again. But the geodesics that stay further away manage to escape. The geodesics that are swallowed continually spiral downward, whereas the geodesics that escape spiral back upwards. Here's another way to think about geodesics. Suppose we zoom in very closely so that the curved space can be approximated as being flat. Suppose we use this approximation to move our arrow forward by a tiny amount. We now correct for the fact that the space is not flat by rotating our arrow along the line perpendicular to the surface. If we repeat this over and over again, we get the path of the geodesic. One thing that all these examples have in common is that the curved space is represented as a two-dimensional surface embedded in a three-dimensional space that obeys Euclidean geometry. This can be misleading, as the curved four-dimensional space-time of our universe does not necessarily need to be embedded in a space of more than 4 dimensions in order for general relativity to work. It could just be that the universe we live in is simply not governed by Euclidean geometry. In cases where we're traveling at a speed far less than the speed of light, and Newtonian physics gives us accurate approximations, contrary to popular belief, the apparent force of gravity has little to do with the curvature of the three spatial dimensions relative to each other. In these cases, the apparent force of gravity is primarily due to the curvature of the time dimension relative to the three spatial dimensions. This is explained and visualized in the video titled "Gravitational Time Dilation Causes Gravitational Attraction." More information is available in the other videos on this channel, and please subscribe for notifications when new videos.
Welcome back. Now at the end, you have a question answer session. If you have any question from today's lecture or yesterday's lecture, you can discuss with me. Our first part of Riemann geometry is finished. Tomorrow we shall start with GR. First SR, then we come to the GR. And the day after tomorrow we shall discuss some cosmology as well as exact solutions. So any questions? You are welcome to ask any question. Well, today's lecture mostly consists of calculations, and I mean mathematical, but even then you can ask any question. Okay, if there is no question, then we close this session. Thank you very much. See you tomorrow. Okay.